Hello, this is Dr. Johnson. I'm one of the AP Stats teachers at Capel High School. Welcome to this lesson on designing experiments. And I promise this one will be shorter than the last one. I hope you have your note-taking assistance sheets in front of you so that you can take notes. As usual, my slides here are to capture some of the most important principles. We still recommend that you read the textbook for further details. First thing I want to talk about is statistical significance. Results of an experiment or sample are called statistically significant if the observed effect is unlikely to be the result of chance variation in sampling or random allocation to experimental groups. That's the key language. The observed effect is unlikely to be the result of chance alone. Remember, what we're looking for is differences that are real and not due to sampling error or just chance. So what's an example? Well, on September 11th, we saw one airplane crash into one of the Twin Towers in New York City. And I was watching TV. They showed this over and over again. And I thought, wow, that is one really bad navigational blunder that someone would hit at one of the towers. Then, a little while later, a second airplane crashed into the other Twin Towers. And I said, no, it's unlikely that two different airplanes would crash into the two different towers. This is something that is not likely to occur by chance. This had to be something that was different. It was terrorism. It was, statistically significant. That's one example. I want to give you another example here. Suppose the average weight of an adult golden retriever is 70 pounds and that 95% of all adult golden retrievers weigh between 50 and 90 pounds. Let W be the weight of adult golden retrievers. Okay. Your friend claims that he saw an adult golden retriever that was 40 pounds. That sounds unusual. How could you explain that? Well, one explanation is that it was an adult golden retriever, and we got one that weighed only 40 pounds by chance alone, and that sometimes happens. Or the other alternative explanation is that it is not an adult golden retriever. How likely is it that we get a randomly selected adult golden retriever that weighs 40 pounds or less? Well, we know that 95% of adult golden retrievers weigh between 50 and 90. So we know that less than 5% of adult golden retrievers weigh 40 pounds or less. And technically, I could write it like this. The probability of getting a W less than or equal to 40 is less than 0.05. So what conclusion are we going to come to? Which of those blue explanations are we going to go with? Well, if we selected adult golden retrievers at random, it would likely weigh between 50 and 90 pounds. Since 40 pounds is considered an unusual weight for adult golden retrievers, it is unlikely that this was an adult golden retriever. The observed differences in weight is considered statistically significant because it is not likely the result of chance variation in the weight of adult golden retrievers. This is the logic that we're going to use for inference testing, but we're going to bring this into, we're introducing it now because this is such an important topic. Every statistics teacher will tell you this: correlation does not prove causation. Correlation does not imply causation. Without a proper experimental design, one cannot be absolutely sure of cause and effect relationship. What you're seeing, the correlation that you're seeing, might be due to chance or other missing variables. To prove causation, we have to meet a very strict standard that the predictors precede the outcome in time, that there's a strong statistical relationship between predictors and outcomes, and that all rival causal factors have been accounted for by design or by statistical control. All three of those requirements correspond to proper experimental design. There's statistical significance and there's also practical significance. What is practical significance, the observed difference between the groups should also have practical significance. Practical significance means that it must pass the who cares test. A small but important real-world difference may fail to reach significance in a statistical test. Conversely, a finding can be statistically significant without being practically important. What's an example of something that doesn't have practical significance? Well, based on a large survey of households in the US, the proportion of households with a pet cat differs significantly from 1/3, but is actually quite close to 1/3. So there's a statistical difference, but really, who cares? That study fails the practical significance test. Inferences about population and causation. To make an inference or conclusion about the population, the subjects that take part in the study must be randomly selected from the population. Okay? To make an inference about the population, we must have random selection. Second bullet point. To make an inference about cause and effect, the individuals in a well-designed experiment must be randomly assigned to treatment and control groups. So cause and effect requires random assignment in an experiment. Lack of realism in an experiment may limit our ability to make inferences about either the population or cause and effect. And frankly, experiments are subject to that criticism that they are sometimes not realistic. So on your note-taking system sheet, you have a table like this. I want you to complete it. Put the yeses and the nos on the table, and then go back and study this. I'm going to suggest that you pause the video right now and complete this, but I'm going to go ahead. Ethical considerations. I just mentioned this because some experiments on humans, run the risk of not being ethical. So the government steps in and they say that all experiments must be screened in advance, the subjects must have informed consent, and any reports on it must keep the individual subjects confidential. The basic idea here is that the US government is stepping in just to make sure that the experiments are safe. Now, a good experiment has several characteristics. This is the first characteristic. A good experiment compares at least 2 treatment groups, one of which could be a control group. All subjects should be treated alike except for the treatments that the experiment is designed to compare. Any other unequal treatment can cause confounding and bias. A good experiment also controls for potential confounding variables. Keep other variables that might affect the response the same for all the groups to reduce confounding. A good experiment randomly assigns or allocates treatments to the experimental units. The groups of subjects must be similar in all respects before the experiment so that we can assume that the differences seen may be largely due to the treatment. Random assignment helps to create roughly equivalent groups of experimental units by balancing the effects of other variables among the treatment groups. And finally, a good experiment uses enough experimental units in each treatment group to reduce chance variation in the results and allow for replication. Remember, there is sampling error within the groups just due to chance in the selection of groups and the assignment of treatments. We should use random assignment and enough experimental units in each group so that any difference in effects of the treatments can be distinguished from chance differences between the groups. Replication can also refer to repeating the experiment with different subjects or in different contexts. To recap, a good experiment allows for comparison, controls for outside factors, randomly assigns the subjects to treatment and control group, and uses enough subjects in each group to reduce chance variation in the results and thereby allows for replication. Let's see how this works. Suppose we want to study whether exercise prevents colds. We select 100 subjects and gather data on each subject's amount of exercise and number of colds last year. Explain how you could use these 4 principles to make a better study. Random assignment. Well, I'm going to randomly assign 50 to the exercise treatment group and 50 to the control no exercise group. That would make this study better. Compare. After 1 year, I record the number of colds for each person and compare the results of the treatment group and the control group. Control. I want to control for outside factors to reduce confounding. So I want this study to have the same geographic area, the same similar age for the subjects, and I want all the subjects to be similar in terms of whether they've had their flu shot. I want to control for these variables. And replicate. I want to use a large number of subjects and repeat the study with different subjects. That's how we use these 4 principles to make this study better. Testing suggestions. I'm going to leave this on your Schoology, this slide set on your Schoology set. On your Schoology page, you can come back to look at this. We'll be reviewing this later prior to the test. That's the end of today's presentation. Thank you very much.